When we speak then of microwave components or microwave devices, RF components, RF devices, what we are implying is that those devices are match devices. They were designed to work within a match system, generally speaking 50 ohms, meaning they are built such that their port impedances, either input impedance or output impedance, is numerically equal to Z0 if all other ports of that device are connected to other quote-unquote matched devices. And so again, we need every device to be matched. If that is true, we can connect it with lengths of transmission line of arbitrary length as with the characteristic impedance Z0, and we'll have maximum power transfer preserved. So these microwave components can have any number of ports. Typically, we find useful devices have 4 ports or less. The most prevalent probably is the 2-port device, and it's easily analyzed. And so let's go through and talk about a 2-port microwave component. Again, a microwave component or device is designed to work in a matched system. It's assumed that it will be attached to some other matched device, whose input impedance, therefore, is going to be numerically equal to Z0. This looks like we've simply connected a resistor of value Z0 to the output of this microwave component, and that would satisfy the requirement that it be immersed in a matched system. But generally speaking, this Z0 is the input impedance of some useful device or some collection of useful devices that are all matched and all connect together, such that the input impedance of any port, and therefore the port connected to this device, is numerically equal to Z0. Likewise, on the other side, we have a matched source here. Again, the matched source is, generally speaking, an equivalent circuit to some microwave component or set of components, a system that is likewise a matched system connected together with transmission lines of 50 ohms designed in a way such that the port impedances are preserved to 50 ohms, therefore maximum power transfer is preserved, and we can then model whatever that is on this side, this useful system or device, as simply a matched source. We know that the output impedance will be equal to Z0 of that device if it is a matched device or a collection of matched devices that are connected together. So this is the equivalent circuit that we have for a 2-port microwave component immersed in a matched system. Again, we assume that our component is matched, or at least over some frequencies the component is matched, as we shall see. It is designed to work in a matched system. We evaluate the performance of this microwave component in a matched system. So this is precisely the circuit that we use to understand the behavior of our 2-port devices. How does it work when we have a matched source connected to one side and a matched load connected to the other? So 1-port and our 2-port microwave component are matched 2-port device that we've inserted in here. At 1 port, we say we have a matched source, and the other side we have a matched load. So we have a situation where energy is flowing out of the source. It's flowing through the microwave component and ultimately being absorbed by this matched load at the other side. Because of that, we refer to the port where the source is attached as the input port, and the port where the load is attached as the output port. Now this can cause problems because right away we want to try to define a power we call the input power and the output power. And we see this a lot, and I'm probably guilty of defining things as input power or output power. But it's problematic because, of course, input power and output power are none of the powers that we've discussed so far. We, of course, never talked about an input power or an output power. We've talked about available power and delivered power and incident power, reflected power, absorbed power. And so when we talk about input or output, we talk about the power at one port or the power at the other port. We have to describe that power in terms of one of these 5 values that we've spoken of here. And this leads to some ambiguity. Sometimes we define the quote-unquote input power in one way, and sometimes we might define it another. We might define the output power in one way, and sometimes in another. One way of defining input and output power that seems relatively obvious is to define input power as the rate at which power is flowing across this port plane. And of course that would be equal to the power delivered by this source, the power delivered by this matched source. Likewise, the output power, it seems relatively obvious, we might define the output power as the rate at which energy is flowing across the output port plane, and that by conservation of energy must be equal to the power absorbed by this load, this matched load. And of course this is then one way of defining input and output, but it's not the only way. Now, with the definition that the quote-unquote input power is the power delivered from the source and the output power is the power absorbed by the load, we can take the ratio of those two things and define a unitless parameter that is generally called gain, the gain of our two-port device. The ratio of the quote output power to input power, more unambiguously defined here as the ratio of the absorbed power to the delivered power. And this would seem like a very obvious value of gain. And for components or devices that are not microwave components or devices that are not immersed in a matched system, this is typically how we define the gain of those two-port devices. But the two-port devices we're talking about here are two-port devices immersed in a matched system. That the source connected to the input is not an ordinary source, it is a matched source. And the source connected to the output is not an ordinary load, it is a matched load. And so for a microwave two-port device, we define the input power as not the delivered power of the source. We define the input power as the available power of the source. And therefore, the gain that we typically use in microwave engineering is this, the ratio of the power absorbed by the matched load to the power available from the matched source. Not the power delivered from the matched source, the power available from the matched source. Now, you might think that this is a distinction without a difference. After all, if we have a two-port component that is a matched component, then the power delivered from a matched source will be equal to its available power. And therefore, the input power defined as the available power, delivered power is the same, of course, if the delivered power is the available power, and the delivered power will be the available power if the input impedance of our two-port device when terminated at a matched load is equal to Z0, as it should be if it is a matched component. But there are two reasons why it might not be perfectly matched at the input. One is we have a device that's not perfectly designed. Remember, we talked about the fact that the input impedance is not going to be exactly equal to 50 ohms. And so there's no such thing as a perfectly matched device. The other reason is sometimes we design our devices such that they aren't perfectly matched at some frequencies. At some frequencies they are, at other frequencies we purposely define them or design them rather so that they're not. These devices are generally speaking what we call filters, microwave filters, and we'll talk more about that later. For example, again, earlier we discussed the fact that the input impedance of a matched component, even when it's immersed in a matched system, a perfect matched system, is not going to be precisely equal to 50 ohms. At some point, there'll be a zero that flips to something else. And so we find that we don't ever have a perfectly matched device. The input impedance isn't exactly equal to Z0. And this is one of the major characteristics of a matched component that we worry about. How well matched is each port when it's immersed in a matched system. And of course, we talked about the fact that we describe these values with the matching with real values like return loss or VSWR. And so we find, because the input impedance, even when immersed in a matched system, is not exactly equal to Z0, we find the power delivered from our matched source is not exactly equal to the available power. It's going to be less, the delivered power is going to be less than the available power of the source, and the input impedance is not exactly equal to Z0. So we have two ways of defining gain. We could define gain as the ratio of the power absorbed by the matched load to the power available from the matched source at the input, or we can define it as the ratio of the power absorbed by the matched load to the power delivered by the matched source at the input. And we just showed that these two ratios will give us different answers. In microwave engineering, though, we typically use this gain defined as the power absorbed by the matched load to the power available from the matched source. Why is that? Well, consider a lossless two-port device. If our two-port device is lossless, then we know the power absorbed is going to be equal to the power delivered. Whether it's a, quote, matched source or not, this is going to be the case. And so for any lossless two-port device, matched or not, we know the ratio of the absorbed power to delivered power is equal to 1. In other words, the gain of a lossless device, when defined as the ratio of the absorbed power to the delivered power, will always be equal to 1, regardless of the frequency of the signal coming in. In contrast, since the available power of the matched source is greater than the delivered power, again, either because the input impedance is not exactly optimal at 50 ohms, or we've designed it such that the input impedance is not optimal at 50 ohms, the available power will be greater than delivered power, and therefore the gain defined as the ratio of the absorbed power to the available power will be less than 1, less than or equal to 1. Sometimes we'll find this value is significantly less to 1 at some frequencies in the case of filters. Other times we find this ratio is just slightly less than 1. Again, if we have a well-matched port but not perfectly matched input port. Again, this gives us more nuance, more information about the device itself, since this value can vary from any value from theoretically 0 all the way up to a value of 1, where for a lost device, this is equal to 1, period. So this causes a little bit of confusion. We define our gain as the ratio of the power absorbed by a matched load to the power available from our matched source, and we find the value can be less than 1, even though the microwave component itself is lossless. Why would the gain, defined that way, be less than 1 if the device is lossless? Remember, if we define the gain as a ratio of the absorbed power to the delivered power, the gain will be equal to 1 exactly if we have a lossless device. But if we define it as the ratio of the absorbed power to the available power of our matched source, we can find the gain is less than 1 even if we have a lossless device, and that causes confusion. How could the gain be less than 1 for a lossless device? Well, the reason is the gain, as defined as the power absorbed by the matched load to the power available from the matched source, that gain, if it's less than 1, indicates the device is not well matched. In other words, the input impedance at port 1, or the input port of our device, is not precisely equal to Z0. The gain comprehends not only how much power is lost or gained in the device, but also comprehends how well the device itself is matched. What is its return loss, or VSWR? To understand then the two types of gains that we've discussed thus far, the power absorbed to power delivered, or the power absorbed to the power available, let's go through a sequence of examples so we can see the difference between those two gains, and hopefully that'll be enlightening. First of all, let's consider a two-port device that is precisely lossless. It cannot absorb any energy. Also, this two-port device is perfectly matched. What does that mean? It means that if we attach a matched load to the output port, that the input impedance of this entire device will likewise be equal to Z0. The port impedances are equal to Z0 if we attach to all other ports impedances that are numerically equal to Z0. And so in that case, what we find, because we have a matched source and the equivalent circuit to all of this is the input impedance is simply equal to Z0, we find that the delivered power and the available power are the same. They are equal to each other when the input impedance is equal to Z0. So under that condition, we have matched and lossless. The gain of our device from either definition is going to be equal to 1. The power absorbed to the power available is equal to 1. The power absorbed to the power delivered is equal to 1. probably easily seen when we see that because it's lossless, the power absorbed to the power delivered is always going to be equal to 1. Because it's matched, the delivered power is equal to the available power, and therefore this ratio likewise is equal to 1. Now let's consider a two-port device that is a matched device, but it is a lossy device. So think carefully about this. We need to work our way through this. It's a matched device, meaning that if we connect to the output port a load that's numerically equal to Z0, a matched load, because it's matched, we know that the input impedance at the input will be equal to Z0 as well. The equivalent circuit for all of this will be equal to Z0 if this is a matched device terminated in Z0. Because then the load of this matched source is a value numerically equal to Z0, all of the available power of the source will be delivered. Because this is a matched device terminated in a matched load, the available power of this source is going to be delivered. Delivered to what? Well, delivered to the input impedance of this structure, meaning that that power, that delivered power, is going to be absorbed by conservation of energy by this structure. Now, if this were a lossless device, we could say the energy absorbed by this entire structure must be absorbed completely by this load, if this two-port device cannot absorb any energy. But in this case, we're saying this two-port device is lossy. It can absorb energy. And so if the delivered power is equal to the available power, and that available power is 37 millijoules per second, then we know this circuit will absorb 37 millijoules per second. Will all of it be absorbed by this matched load? Well, we don't know. Maybe half of it will be absorbed by this two-port device and the remainder absorbed by the matched load. Maybe all of it will be absorbed by the matched load and none of it, the matched device, but none of it will be absorbed by the matched load. We don't know. Generally speaking, then, we would say if this can absorb energy, the matched load then will not absorb all of the delivered power. The absorbed power, therefore, will be less than the available power. So again, we're extracting energy at the maximum rate, but not all of that energy is being absorbed by this load because some of it's being absorbed by this two-port device because, in fact, it is lossy. And so when we go through and we look at our gains here, we find that the ratio of the power absorbed to the power available is equal to the power absorbed to the power delivered. Why is that? Because the available power is equal to the delivered power. We have a matched device terminating a matched load. The delivered power and available power equal to each other. Both of our gains have exactly the same value. But because this is lossy, that value will be less than a value of 1. Now let's look at a two-port device that is lossless, but it is not a matched device. What does it mean when we say it's not a matched device? Well, we terminate this two-port device in a matched load, and we find the input impedance is not equal to Z0. So what do we make of this? We know if it's a lossless device that the power delivered by this source will be absorbed by the load. The lossless two-port device cannot alter the rate of energy flow, and those two values, delivered and absorbed, are the same. And therefore the gain defined as the ratio of the absorbed power to delivered power is going to be equal to 1. Again, because it's lossless, it's always equal to 1. This gain is if we have a lossless device. But what about the gain defined as the power absorbed by the matched load to the power available of the matched source? In this case, because we don't have a matched device, the power delivered by our matched source will be less than the power available. We're not extracting the energy at the maximum rate because this input impedance is not equal to Z0. It's not equal to the complex conjugate of Z0. We don't have a conjugate match. And so delivered power is less than the available power. Well, if the power absorbed to power delivered equal to 1, and the delivered power is less than the available power, then we know the ratio of the power absorbed to the power available will be less than 1. And that's what we find when we have a lossless but unmatched device. And hopefully this kind of shows why we define gain in this way. If we define gain in this way, there are two ways that we have a gain less than 1. One is if we have a matched but lossy device. In that case, this gain would be less than 1, as would this gain. But if we have a lossless but unmatched device, this gain will also be less than 1, even though this gain will be equal to 1. And so this gain, defined as the ratio of the absorbed power to available power, is 1. When it's less than 1, tells us that the device is either lossy and or not perfectly matched. It comprehends both of those phenomena. Summarizing then, the gain defined as a ratio of the absorbed power to the available power provides a measure of both the power lost to heat, in other words, absorbed by the two-port device itself and not then delivered to the load, and the power, quote-unquote, lost to mismatch. What we find when we define the gain this way, the absorbed power to available power, the gain is equal to 1 if the component is both lossless and matched. If we use the gain defined as the power absorbed to the power delivered, what we find is it's equal to 1 if the device is lossless, regardless whether it's matched or not. So again, this gain is useful to us in the majority of situations in electrical engineering when we're not concerned about maximum power transfer regardless of the length of transmission line. If we're not using transmission lines at all, it doesn't really matter to us. We typically use this gain. But in a microwave system where we're concerned with preserving maximum power transfer, we use this gain because it provides an indication of both whether the device is lossless and is matched. Now let's go back and look at this idea that we have power loss to mismatch. Sometimes this causes problems, and this is a little bit confusing, kind of a little bit misleading. By lost, we mean sort of a lost opportunity. Let's say you were walking down the street and you had a $20 bill in your pocket and you pulled out your phone and the $20 bill fell out on the sidewalk and blew away and it was lost forever. That'd be lost money. On the other hand, let's say you had someone gave you a gift card, for Starbucks or something, and you used his $50 gift card and you used 30 of it, and then you never got around to using the last 20. It's stuck in a drawer somewhere, and you never ended up spending it. Was that a lost $20? Well, it kind of was. You had $20 and you didn't spend it. It was a lost opportunity. You didn't spend all of the available money that you had, and that's what we have when we have a mismatch. We're not extracting all of the available power of the match source. We're only extracting part of the available power of the match source. The delivered power is not equal to the available power, and that's a lost opportunity. And that's what we mean by loss with respect to mismatch. Now let's explore a different way of defining our gain or describing our gain. What we're going to do here is take our match source and we're going to put a length of transmission line, characteristic impedance Z0, between our match source and the microwave component. Likewise, we're going to take the same characteristic impedance transmission line Z0 and insert a length between the matched microwave component and the matched load. Now, we've really not changed the circuit at all. Remember, the input impedance for a transmission line terminated at a matched load is always going to be equal to the same impedance Z0. And so this is maybe more physical. Maybe this is really what is our matched load terminated. It's the equivalent circuit for a length of transmission line terminated in Z0. The same thing for a length of transmission line attached to a matched source. If we determine the equivalent source here, if we were to use this transmission line as a source transformer, the transformed source, of course, would likewise have the same source impedance, Z0. A matched source connected to a transmission line of characteristic impedance Z0 is transformed into a new source with the same impedance Z0. Just like the load impedance is transformed to an input impedance of Z0, the source impedance is transformed to a new source impedance of Z0. So really this is the same circuit that we've used before. But by writing it this way, it allows us to consider the incident and reflected wave on each of these two transmission lines. We're able to then go back and redefine our gain in terms of the incident and reflected waves on those two transmission lines. First of all, we start with the incident power. What is the power associated with the incident wave on this transmission line? We have a special case where the source attached to the transmission line has a source impedance numerically equal to its characteristic impedance. And of course, we call that the match source. One of the things we know if we have a matched source is that the power incident along this transmission line must be equal to the available power of this source if and only if it is a matched source. And so we can say that the available power from a matched source is equal to the power incident along this transmission line. Now let's look at the right side of our circuit here. We had a match load connected to the microwave component on the output there. But of course that match load is an equivalent circuit for some other useful circuit. And let's say that circuit is a length of transmission line that is terminated in a match load. And of course we know in this case that the input impedance is going to be equal to the characteristic impedance Z0 regardless of the length of the transmission line. So this is the same circuit we had before. We still have terminated our component in a matched load, in this case a more sort of extensive match load structurally, again length of transmission line terminated in a resistor equal to Z0. The reason we do this is now we can talk about the incident power flowing along the line, in this case incident on the load here at the end, and the reflected power from that load. Of course, we know since this load is numerically equal to Z0, it's a special case, and the reflected power in this case is equal to 0. And so on this side of the transmission line, we know that the incident power, the power incident on this load, the power associated with the wave propagating in this direction, is equal to the power absorbed by this load. Why is that? Well, we know the power absorbed by the load is the difference between the incident and the reflected, and therefore if the reflected is equal to 0, then the absorbed is simply equal to the incident. So see what we did here. In the first case where we have a matched source, we know immediately that the incident power, the power incident on the input port, is equal to the available power of this source. On the other side, because we have a matched load, we know the power incident on this load is equal to the absorbed power of this load. So we're going to take those results and insert them back into our gain equation. So we take our gain equation, the ratio of the power absorbed by our matched load to the power available from our matched source, and we have, since we've gone through and talked about the available power in terms of the incident power on the input port here, and the absorbed power in terms of the incident power on the load here, we can insert those results and also write the gain of our microwave component in this form. And this is also a very common way of writing the gain of a two-port device. The ratio of the power incident on the input to the ratio of the power that is essentially exiting this port and therefore incident on this matched load. So here's an alternative way of writing the gain of our microwave component in a way that is very common to describe it in this way. If we had a two-port device that was both matched and lossless, and we connect a matched source and load to it, then we know that the power available from the source is the power absorbed by the load. The power delivered from the source is the power absorbed by the load. If this device were both matched and lossless, the gain would be equal to 1. But let's say we have a situation where this two-port device is lossless, but it is not perfectly matched. In that case, we have a situation where the input impedance for this one-port equivalent circuit here, this input impedance would not be precisely equal to Z0, even though we terminate down here the output port with an impedance of Z0, the input is not quite Z0 because it's not perfectly matched. The result of that is we have some reflected power here. The net power is the difference between the incident and the reflected, and therefore that net power is less than the incident power. And of course the incident power is equal to the available power of the source. So in other words, the net power is less than the available power. Now that net power, if this is lossless, is going to be absorbed by that load, which means that the power absorbed by the load, which is equal to this, will be less than the available power of the source. Again, we get this idea of loss. It's not loss from the standpoint of something's heating up, the way we have a loss in a lossy device that turns electromagnetic energy into heat. No, in this case, the loss, again, is sort of a lost opportunity. We could have extracted more power, but we didn't. And the reason we didn't is because the impedance that this match source is connected to is not perfectly a match load of Z0. What we see here is that loss essentially is reflected, no pun intended, in the reflected power here. If the input impedance is not precisely equal to Z0, then we have some reflected power. And the difference between the incident and reflected power then is going to be the net power, and thus the power absorbed. And you can see the power absorbed is less than the available power if that reflected power is non-zero. And that will happen if we have an unmatched lossless component. And so again, the loss due to a unmatched device we can sort of speak of with respect to the power associated with the reflected power here at the input port. If that reflected power is zero, then we have no quote-unquote loss. Not loss associated with absorption. Again, this is a lossless device, but again, a loss meaning the absorbed power is less than what we could have gotten, less than the available power. And of course, the ratio of the reflected power to the incident power is the return loss, and that's why we call the return loss a loss. Ideally, of course, the return loss is infinite infinity. That's the best situation, and that implies or means that the reflected power at this input port is equal to zero. So the mismatch causes reflected power, and the absorbed power is therefore reduced. Not all the incident power comes in, some of it's reflected, and the amount that's reflected ultimately manifests itself in a reduction in this absorbed power that's less than the available power of this match source. Finally, we point out that the gain of most microwave devices are expressed with the decibel operator. And the decibel operator is simply an operator on the gain. It must be, the argument of the decibel operator must be a coefficient. It must be uniless. And simply 10 log 10 of this uniless value gain. And in this case, the gain, if we define it as the ratio of the absorbed power to the available power, then it is 10 log 10 of that ratio. The decibel operator, as we'll talk about later, is always equal to 10 log 10. If we have 20 log 10, we don't have a decibel operator. All right, so there's no ambiguity there. There's always a situation. Do you define decibel in terms of 10 log 10 or 20 log 10? Well, 20 log 10 is a result, but it's not the decibel operator. 10 log 10 that we have here on a uniless value gain. If we have a lossy or lossless device, then we find that that gain is always going to be less than 1. And so in decibel, we find the gain will be less than 0. In other words, it'll be negative. When we express the gain of a lossless or lossy device, we find the gain is going to be negative. If we have an active device, we might have a situation where the power absorbed is greater than the available power if we have an amplifier. And in that case, the gain, when expressed with the decibel operator, is a positive value. And we'll talk more about gain later. I'm sorry, decibels later.